going to do is I'm going to start out spinning, and I'm going to have my arms in like this. My axis of rotation is basically somewhere around here. When I move my arms outwards, what happens to my moment of inertia? As mass gets farther from the center, what happens to moment of inertia?
It gets smaller.
Sorry, I heard several things, but
Weakens.
It weakens?
weakens. If you recall, moment of inertia is just the sum of a whole bunch of mr squared. So mass times the distance squared. So if I take this mass and move it farther away,
Then it gets greater.
it would have to get greater. So the farther the mass is away from the center, as it's spinning, the greater the moment of inertia or rotational inertia. Since the moment of inertia goes up, then in order for my angular momentum to stay the same, my angular velocity or angular speed is going to have to get smaller. So as one goes up, the other gets smaller in a closed system. Now, officially it's not a closed system because there is friction here. I could spin around and I will eventually stop without doing anything else. However, nice to have something. Let's see how well this works. Then I slow down, and then I speed back up again. Take a moment. All right. From a force point of view, as I'm spinning around like this, this arm, as my body is rotating this way, this arm is rotating in the opposite direction. So what's happening is that as I'm spinning up, I'm basically throwing an arm backwards, which is, from a force point of view, what's slowing me down. This arm is basically doing something similar. Let's see, as I'm spinning, that gets thrown backwards. This one is in essence just going out. As I'm spinning around the other way, so I'm going like this one arm is, I'm pulling all the way over, so I'm sort of slinging myself more into that direction. This arm is just coming straight back in. So as I pull in from a force point of view, I'm sort of throwing myself in the direction I'm moving, and so I speed up. So let's just do a quick plug and jug. So I've got this rod. As the rod spins, it slowly slips. I've got it on some sort of holder as it's spinning around, and as it's spinning, the thing slowly moves out. So, think about moment of inertia. As the moment of inertia is spinning about the center, it's related to the mass and how close the mass is to the center. And as the bar slips out that way, will the moment of inertia go up or down?
Up.
Because there's more mass farther away. So if it does this, well, my total momentum, angular momentum beforehand, we just erased or just disappeared. 282. No. What was that? It was 0.282.
0.6282.
Or 6.2.
Like 1.5 times 0.4188. Oh yeah, 0.6282. Is that it? Okay. All right, so beforehand, 0.6282 kilogram meter squared, radians if you want them per second. Okay, so as the bar slips out, the moment of inertia is going to go up. So there's a new formula. If I take that same bar, so this is the rod rotating about its center. If I took that same rod, rotating about it in, so rod about in about the Canadian fans out there, about in, the formula changes to 1/3 ml squared. And that's something that we have to give you. It's simple enough to derive, but beyond scope of this course. But if you're interested, I'll be glad to show you afterwards. So my moment of inertia becomes 1/3 times my mass of 2 times my length of 3 squared. Just 6. That sounds about right.
Yeah.
Kilogram meters squared. So what is my final angular speed? Well, that's going to be my angular momentum stays the same. That's what it was before. It's got to be that afterwards, and that's going to be equal to my moment of inertia. Times my angular velocity. We'll just assume it was traveling in the positive direction to begin with. So the math problem is 0.628 equals 6 omega. That's the math problem.
So you divide by 6.
Yep. And we're left with omega equal to 0.14.
I got 1.1047.
1047 units.
They're both kilogram meters per second squared. Meters per second squared over kilogram meters squared divided by seconds, right? They both.
That's what that was. That 6 is just kilogram meter squared.
Kilogram meters squared. Oh, I put it per second on the bottom. So seconds. No? The 2 kilogram meters squared cancel out, right?
Yeah.
And then you're just left with the seconds that it was divided by for the 0.6282.
So this is
No.
unit. We have kilogram meters squared per second divided by kilogram meters squared.
Aren't you just left with seconds?
What is this equal to? It's not seconds.
What am I doing wrong?
So if I take my kilogram meters squared per second divided by kilogram meters squared.
Is it 1 over seconds?
There we go.
Okay.
That's the same as kilogram meters squared per second times 1 over kilogram meters squared, and I'm left with
1 over x.
except 1 over seconds is somewhat misleading. Because we're talking about an angular thing and not there's something, 1 over seconds by itself is a hertz, but this is not hertz. What did we just sort of ignore, but now we have to bring back again? The unitless unit.
Rads?
It's radians per second. And this is one of those things, there was a radians here that I ignored. Yeah, so that radians I didn't write when I came to the other side, but it's there. It's in there.
So do we have to write rad or no?
You should. If you don't write the rad, technically it's not wrong, but it would be confusing to someone looking at it quickly.
Okay. So where was rad supposed to be? Next to,
It's radians per second.
like before that?
Oh,
Where was it supposed to be?
radians was right there. Because we multiplied kilogram meter squared times radians per second.
Oh,
So that's why.
okay.
And again, typically you drop radians when you multiply it by something and you make sure it's there when appropriate. Which is not exactly a hard and fast rule.
Okay.
Questions?
So when do you not put rad, or when do you put rad?
If I'm dealing with, I know that angular speed, angular velocity is units of radians per second, so I would put the rad in there. You typically, if
But if it's
it's
inertial,
rotational stuff, then you might think, okay, is there some place where it doesn't seem like there's a unit?
okay,
Let me put radians in there.
because we just had sec 1 over s, and it just
Yeah,
wasn't specific.
1 per second is.
Okay.
Yeah, 1 per second would make someone think that it is a frequency and not an angular frequency.
Okay.
But again, it's like Newton meter sometimes is joules and sometimes it's not.
Okay.
So we've talked about torque. Well, actually, let's take a break, come back, regroup. We'll talk about torque. We'll put a stake through the heart of chapter 8, and then we'll finish up through 10 before we're done today. We've already done parts of 9 and 10. We've done all of 10? Maybe. All right, if you looked in the book, the formula that the book has for angular momentum is not the same as what I had written there. One, he doesn't use vector notation, but he gives a different formula. So I want to connect those. We talked about earlier that the speed of an object, if I have something spinning around, the speed of a point. So as I spin this around, everything in the bar, assuming my arm stays rigid and the bar is rigid, everything in the bar travels with the same angular speed. But the velocities are not the same. The parts on the outside have to travel farther than the parts on the inside. And we had the formula that the speed is equal to the angular speed times the distance to the axis of rotation. So this would be distance to axis of rotation. That's angular speed.
And that's the textbook equation.
That,
The V equals.
yeah, I mean, it's in the textbook. That's not ultimately, the textbook has the angular momentum is mvr.
Okay.
So I gotta do a couple things here.
Okay.
That's one of them. The other bit is, if you recall, when we were deriving our formula for moment of inertia, it was equal to the sum of I equals 1 to however many particles you have, mr squared. So you basically, you think of the object as a bunch of tiny little particles, and do the r from axis of rotation, which I guess my shoulder right now, to where each part of that, each little bit is, add them all up. Now, they did a whole bunch of them with formulas there, but I specifically want to look at if I have a point mass. So if you think about the satellite again, Earth and satellite. Satellites, for the most part, might be big compared to us, but they are tiny compared to the Earth. Not talking about the moon, I'm talking man-made satellites. Man-made satellites, tiny compared to the size of the Earth. So from the Earth's point of view, that can be considered a point mass. And what I mean by point mass is the distance from the center to the closest point and the distance from the center to the farthest point is so incredibly small, the difference is so incredibly small, we count it as it's in a single location. And so if it is a point mass, then I have only one mass, because we're considering it all in one location, times r squared. So if point mass so the angular momentum of a point mass would be, well, the magnitude at least, is I, so that's mr squared, that's my moment of inertia for just a single point rotating, times omega, well, omega is just gonna be v divided by r. Since v equals omega r, omega is v over r. That r cancels out with that one, and I'm left with mvr, which is what Hewitt has as the formula. Just realize that formula only works if the size of the object is tiny compared to the radius of the orbit or rotation.
So it's absolute L equals M R V.
VM or NVR.
MVR, okay.
All right. So I wanted to hit on that point. Now let's talk about G2 Kabuka. We did a lab similar, we did a lab, second lab, I think, where we looked at forces. So that the forces up should equal the forces down. We now have a little bit more at our disposal. So if I've got a beam here being held up by two ideal pieces of wood, we'll give the mass of the beam to make it 10 kilograms. Let's give some lengths here. So that distance there is 4 meters. We'll make that distance 1 meter, and that distance 2 meters. So that leaves 1 meter in this. So that's 1 meter. Obviously, not from the scale. So let's take a look at what are the forces acting down, or the force diagram. What are the forces acting on the beam?
Down due to gravity? No,
What did you say that again?
I said down,
Is what's acting down?
the force of gravity.
Oh, force. Okay, I missed force up. All right, or weight. So I have weight acting down. What's acting up?
The weight acting up onto the beam? No,
There's a weight acting up on the ground,
on the ground.
but on the beam. Forces acting on the beam. What's acting up?
The tension from the rope?
Yeah, and I have two tensions there. So I have I'll call it FT1. Actually, I call it FT1 and FT2. Let's put this on what I refer to as Earth 2, which means that on some planet where G is 10 meters per second squared, little g. So what is the weight of the object, of the beam?
Would it be 10 times 9.798?
It wins the sale, yes. On Earth 2,
Oh, 10 times 10.
yeah. So my weight is equal to 100 newtons. So I've got these two forces acting up. I don't know exactly what they are right now. I mean, it could be 50 and 50, but probably not. Because this rope right here is closer to the center than that one is. Is it 40-60? Maybe. How do we know? How do we figure out what this actually should be? Well, 50-50. Based on what we did in chapter 2, it could be either of those answers. So let's take a look at torque. This is in static equilibrium. There's no acceleration, there's no angular, it's an angular, static angular equilibrium as well as linear. It's just sitting there. So static meaning not moving. So I know that the acceleration of the beam is 0, or the total torque, total force is 0, that the change in velocity is 0. So that's all equilibrium. And then for the static equilibrium, it also says that the velocity is 0. That's chapter 2 stuff. Now we're more sophisticated, we can bring in some rotation. So rotational static equilibrium. Well, rotational equilibrium, well, we're just gonna transliterate here. Instead of A, it's alpha. So alpha equals 0 radians per second squared. Torque total is equal to 0 Newton meters. And the change in angular velocity is equal to 0 radians per second. This is all rotational equilibrium. And then the static part tells us that the angular velocity is also 0.